Welcome. In this lecture video, we're going to take a look at the equations of motion for simple harmonic motion. And we're going to focus on springs in this one. So in the past, we've looked at simple harmonic motion or spring motion just based on position and energy. And we've used conservation of energy to solve for things like maximum velocity, maximum amplitude, things like that. So this time we're actually going to derive some equations of motion that will allow us to tell where this oscillator is at different times t. Not only that, but the velocity at any time t, the acceleration at any time t. Okay, so first we have a block on a spring, and we're going to assume that this spring has a spring constant of k. And we see that this block right now has been displaced, displacement x from its rest position. So we have a force F from the spring that arises in the opposite direction of the block's displacement. So going back to our tried and true Newton's second law, we have the force from the spring is equal to negative kx. And this is this is Hooke's law. Applying Newton's second law, since F is equal to ma, we've got the mass times the acceleration is equal to negative k times x. And remember that the negative sign comes from the fact that the force is in the opposite direction of the displacement. The block was displaced to the right, the force is going back to the left. So there is the negative sign. So let's do a little math here. We're going to divide both sides by m, so we get A is equal to negative k over m times x. And we want an equation of motion here. We want a position with respect to time. And we go back and recognize that A is the derivative of the velocity. It is the second derivative of the position. So if I say it's d squared x dt squared, the second derivative of the position, and that's equal to negative k over m. And here we have a differential equation. It's different from the differential equations that we have seen before because this one is a second derivative, not a first derivative. There are techniques to solve this differential equation, and you will learn them when you take Diff-EQ. But for right now, we're going to look at what possible solutions of this would look like. All right? The takeaway from this is we know that a spring is a simple harmonic oscillator. And this right here is something that should ring alarm bells in our head in the future, because this is the requirement for simple harmonic motion. If we ever have the second derivative of position proportional to the position, the opposite of the position, then we're looking at simple harmonic motion. All right, so the conditions required, or conditions necessary for SHM, simple harmonic motion. And we're going to see this again when we take a look at pendulums. So here let's take a look at three things that at first don't look like they have anything in common. We have a cart attached by two springs, we have a pendulum hanging above that cart, and then we have a turntable down below that that is rotating a constant angular velocity. And when we set these guys in motion, when I actually do set them in motion, what we see here is, wow, the frequency of oscillation back and forth of all three of these things is intimately related. The pendulum goes back and forth at the same rate that the cart does, at the same rate that the turntable does. So these three kinds of motion, uniform circular motion, simple harmonic motion with springs, and pendulum motion back and forth, are related. Now let's take a look at, if we actually graphed these, what that would look like. I hit the wrong thing. So here we're just looking at the cart. And the cart starts out at x equals 0. Up above, we have a position versus time graph, we have a velocity versus time graph, and we have an acceleration versus time graph. So we start this thing in motion, and based on those graphs, we can see that the solution we're looking for simple harmonic motion certainly looks like it's a sinusoidal function. The position graph starts at x equals 0, and it goes up to a maximum value at that pi over 2 value. Then we're at pi, we're at 0. So we're definitely looking at a sinusoidal graph. So I'm guessing that the solution to our differential equation that we saw there is sinusoidal. Not only that, take a look at the relationship between position, velocity, and acceleration. We already know that the derivative of velocity should be, the derivative of position should be velocity. Well, where do we get a maximum slope in our position graph? At x equals 0. Where is the velocity at a max? At t equals 0. Okay, where do we get a 0 slope on our position graph? At that pi over 2 spot. And where do we see our velocity equal to 0? At that pi over 2 spot. All right, and bringing in some other ideas here, what we see here for the position, we can find the time that it takes to do one complete oscillation by looking at that right there. And as you go down right here at the labels on this graph, that's given a big T, the period of motion, the time for one complete cycle. Okay? So it looks like our solutions are going to be sinusoidal. If we take a look again at the position graph, this would for sure be a straight up sine graph. The sine graph starts at 0, goes up to its max at pi over 2. If we started this oscillator instead at a different position, let's say that we started it at one of the amplitudes, then you could see we're here at the positive amplitude. We would start our graph right here. I need a pen. We would start our graph right there. And if we start our graph right there, wow, that certainly looks like a cosine graph. The cosine graph starts at the amplitude and goes down to there. And again, that would be one complete period, that blue line right there. So one complete period, and we also see that whatever this is, that's going to be the amplitude of our cosine or sine function. Okay, so let's take this knowledge that the position versus time function for this should be a sinusoidal function, and we'll go back to our differential equation. Okay, so here we have a position versus time graph, and this could be the spring oscillator. And instead of starting the graph and the oscillation at x equals 0, I've chosen to start my oscillation at the positive amplitude. And usually with springs, that's what we do. We pull the cart one way or the other, and we let it go. So that's what we have done. We've pulled the cart one way to its positive amplitude and let it go. So we take a look at the general cosine graph. We would have x of t is equal to cosine of something times t. Okay, so if this really is the general cosine graph, and this position right here then would be 2 pi, then that's it. We'd also have the amplitude here would be 1, right? But that's not actually what we see with our oscillator. Instead of 1 right here, we have an amplitude. We have x max, the maximum position away from the rest position. So in our function here, instead of writing a 1 in front of the cosine, we're really going to have x max, or the amplitude. So that completes things here. Now, our period is not going to be 2 pi seconds. Our period is going to be something other than 2 pi. And so this is going to cause some issues inside the parentheses of our cosine function. And what we're going to see is that there is some, we can show mathematically that our argument inside of the cosine function, the t has to be multiplied by this omega. And we've seen omega before, angular velocity. And if we go back to our simple harmonic motion, this guy right here, and we press play, we can see that we do have a circular motion down here. And if we found the angular velocity of that in radians per second, we would see that it gives us a kind of angular frequency, the omega that we're going to have inside that. And we could graph, actually, the same way that we graphed the spring position, we could graph the back and forth motion of that little flag that's on the disk. We could graph that as well with a cosine function. And we're going to see that the angular velocity there is going to be what's inside of that cosine. All right, so let's head back. So bringing in our differential equation again here, remember we had d squared x dt squared is equal to negative k over m times x. And it can be shown mathematically. We're not going to do it. It's beyond the scope of this lecture in this class. But that whenever we have this situation, remember the second derivative of position is proportional to the opposite of the position, then we end up with the conditions for simple harmonic motion. And we see then that negative omega squared is equal to whatever comes in front of our position, that proportionality. So we have negative k over m. And the negatives cancel, and we end up with omega is equal to the square root of k over m. Now this is true for springs, and omega is called the angular frequency of the oscillation. And just like in circular motion, omega is in radians per second. And omega also does have a relationship to the actual frequency, the cycles per second. Notice that there's a unit of radians there. So how do we get rid of the radians? Well, if it's radians over seconds, and instead we want cycles per second, simple conversion, there's 2 pi radians in one complete cycle. So it looks like we have to go ahead and take omega and divide by 2 pi to get our standard frequency. So omega over 2 pi is equal to what we traditionally think of as the frequency. And the unit on that frequency is cycles per second, or hertz, 1 over seconds. Okay? So we are at a nice little point here. We do have now a function that will graph the position of this spring oscillator at any time t, understanding that omega for the spring is equal to the square root of k over m. Oh, one quick little aside here. The omega equals square root of k over m here. You can simply see with this equation that if we increase k, if we increase the stiffness of the spring, then we're going to increase the frequency of the oscillation. That thing's going to oscillate back and forth more frequently. And also, similarly, if we increase the mass, the bottom of our denominator gets larger, so our overall value for omega gets smaller. We will slow down the oscillation if we increase the mass. So the frequency of the oscillation is dependent on k, and it's dependent on m. All right, so let's move in and develop our velocity and acceleration functions as well. So here's our point. We have x of t is equal to x max times cosine of omega t. And now we know that the velocity at any time t is equal to the derivative of the position function with respect to time. So we take the derivative of that. The derivative of cosine is the opposite of sine. So we're going to have negative x max times the sine of omega t. However, we took the derivative. We have something inside of our parentheses here. We have to use the chain rule. We have to multiply that by the derivative of the stuff inside. The derivative of omega t is omega. So we have negative x max times omega, sine omega t. There is our velocity function. Doing it again, the acceleration is the derivative of the velocity, so dv dt. And we take the derivative of that. Derivative of sine is cosine. And again, we're going to have to use the chain rule. So we end up with negative x max omega squared now cosine of omega t. And those right there are our 3 equations of motion for this oscillator. It's a spring, a mass on a spring, and we remember here that omega is equal to the square root of k over m. And remembering also, going back one page, our omega divided by 2 pi is equal to frequency. So we can say that omega over 2 pi is equal to the traditional frequency. So if we know omega, hey, great, we can find the frequency. And we remember also that frequency is 1 over the period. Those are reciprocals of one another. So if we know the frequency, we've got the period. All right? So things you're going to be asked to solve for: the position, the velocity, the acceleration at any time t. If you're given k and m and x max, then you can give the equations of motion. You can solve for the spring constant if you know things like x max and a position at any time t. You can solve for things like the mass. If you know the frequency, you can find omega. All sorts of fun that we can have with these. All right, so we're going to put these equations to use next time. Thanks.